So now we are going to solve equation 1, and it's about this equation says x double dot plus lambda x equals 0, and we have found our boundary conditions for this big X function. So basically big X function at x equals 0 equals to 0, and big X function at x equals 1 equals to 0 as well. Okay, so now we are going to consider the three possible values for our parameter lambda. Okay, so we have lambda equals to 0, or lambda can be a negative number, or lambda can be a positive number. Okay, so let's say lambda equals to 0. If lambda equals to 0, this differential equation becomes x double dot equals to 0. Now to solve this, we just need to integrate twice. So if you integrate once, then you will get x dot equals to a constant, let's say c1, and we have to integrate this one again to get the solution for big X. So then you will get big X equals to c1x plus c2. Okay, now let's say when x equals to negative a squared, then my differential equation equals to x double dot minus a squared big X equals to 0. Now at this point we know the solution of this one. So basically big X of x equals to some constant, let's say it's c3 times, let's use the exponential solution, so c3 times e to the ax plus c4 times e to the negative ax. So here if you want, you can write the solution using the hyperbolic trig functions as well. So if you want to do that, then maybe so O should get c3 tilde hyperbolic cosine of ax plus c4 tilde times hyperbolic sine of ax. Okay. Now if lambda is a positive number, then my differential equation is x double dot plus a squared times big X equals to 0. Now if you solve this, we get big X of x equals to c5 times cosine ax plus c6 times sine of ax. Again, all these differential equations are second order constant coefficient differential equations that we can solve using the techniques that we learned from the first part of the ordinary differential equation course. Okay, so next what we do is we are going to figure out the values of these unknowns or these constants using the boundary conditions. Okay, so let's consider the first solution. Okay, so when x equals 0, my function big X should be 0, and if you evaluate big X at 0, this is c1 times 0 plus c2. So basically this is c2 equals to 0. Now let's apply the second boundary condition. At this point we know that c2 is 0. If we evaluate big X at 1, then we have c1 times 1, and c2 is 0, therefore c1 times 1 equals to 0, this is c1 equals to 0. It means when lambda equals 0, our big X function should be equal to 0 in order to satisfy these two boundary conditions. Okay, so use a different color. So then big X of x should be 0. Now let us consider the second case where lambda equals to a negative number. Okay, so we have the solution for our function big X of x. Now let us apply the same boundary conditions. Okay, let me use a different color. Okay, big X at 0 equals to, okay, from this we have C3 times e to the 0 which is 1 plus C4 times e to the 0 which is also 1. So we have C3 plus C4 equals to 0. Okay, so this means C3 equals to negative C4. Okay, now let us apply the second boundary condition. When x equals 1, your big X function equals to C3 times e to the a plus C4 times e to the negative a, and this equals to 0 as well. Since C3 equals to negative C4, we can write this equation in terms of the C4 variable only. So we have negative C4 e to the a plus C4 e to the negative a equals to 0. Let us factor out C4 from this. So we have C4 times negative e to the a plus e to the negative a equals to 0. Now this term does not equal to 0, therefore the only possibility is that C4 must be 0 as well. So C4 should be 0. Okay. Again, so since C4 equals to 0, then C3 must be 0 as well, because C3 equals to negative C4. Now if we go back to our solution big X of x, C3 is 0, C4 is 0, therefore this function is identical, equal to 0. Okay, so now let me write it here, big X of x equals to 0. Okay, now let us consider the third lambda value. Here lambda equals to a squared, and we have already found the solution. Big X of x equals to some constant times cosine ax plus another constant times sine ax. We are going to apply the boundary conditions. When x equals 1, big X equals to, when x equals 0, we have C5 times cosine 0 plus C6 times sine 0. Sine 0 is 0. Okay, by the way, this equals to 0. Sine 0 is 0, cosine 0 is 1. So basically we have C5 equals to 0. Okay. So next we are going to use the second boundary condition. When x equals 1, okay, now since C5 equals to 0, we do not have to consider the first term. We have the second term, C6 times sine of x equals to 1. So we have sine of a equals to 0. Okay. So now we are looking for the non-trivial solutions. For the first case and the second case, we have obtained trivial solutions where big X equals to 0. Okay. Now since we are looking for non-trivial solutions, in this problem, in this third case, Cx cannot be equal to 0, because if C6 equals to 0, then we are going to get the trivial solution. Okay, so C6 cannot be equal to 0, but we want this product C6 times sine a equals to 0. So, if C6 does not equal to 0, it means sine of A should be 0. Now, at this point we do not know the value of lambda, therefore, we do not know the value of A. But in order to satisfy this equation, our A should be a scalar multiple of pi. Our A should be a scalar multiple of pi. So, I denoted that scalar using n pi, and here my n goes from 1 to up to infinity. Okay. Great. By the way, if n equals 0, then we are going to get this one, because if n equals 0, then we have A equals to 0, therefore we have the first case. Okay. So, now we have found a value for A, and now let us go ahead and update our function big X. Big X of x equals to, so this is 0, we have C6 times sine of Ax, but A equals to n pi x. Okay. And since we know the value of A, we can calculate the value of lambda. So, lambda equals to A squared, but A equals to n pi, therefore, lambda equals to n squared pi squared. Okay. Great. So, now in this part what we did was we solved the first equation, which is given here, x double dot plus lambda x equals to 0. Next we are going to solve the second order ordinary differential equation that we obtained for the big T function.